Welcome viewers. Today in this part of the course we are going to have a review of signals and systems. Signals are any kind of information signal which carry messages which are important to a communication system, and the channels can be modeled as some linear time invariant systems. So, today in this part of the course we are going to have a review of concepts related to signals and systems. The outline for the today's talk are: first we will discuss different kind of signals which are important to communication systems, then we will define what is a linear time invariant system and how the signals, when they pass through the linear time invariant system, what the output will look like, and then we will talk about a concept which is waveform spectra. Signals. So, signals are mapping on sets, and what we are interested in, the signals which represent information. The examples of these signals are audio signals which map the time to air pressure. These audio signals represent sound perceived by humans. Another example for signals is video signals or image signals. Image signals represent region of space onto light intensity. Images carry information perceived through human vision. Another form of signals which are very common to communication systems are radio signals. Radio signals is a mapping of time to electromagnetic waves. Radio signals carry information of all types and must be converted into signals which are perceivable by humans. Now, we are going to review some of the very important basic signal types which we will be encountering throughout this course. First of them is a sinusoidal signal. A sinusoidal signal is a periodic function of time of the form st is equal to a cos 2 pi f naught t plus theta naught, where a is the amplitude of the signal, f naught is the frequency and theta is the phase. This complex sinusoid for different values of phase can be converted into a pure cosine wave or pure sine wave. Value of theta is equal to 0 will result in a pure cosine wave, and theta is equal to minus pi by 2 will result in a pure sine wave. Another signal which is of importance for us is complex sinusoid or complex exponential. A complex exponential signal for a frequency f naught is given by st is equal to a e to the power j 2 pi f naught t plus theta. This can also be represented as alpha times e to the power j 2 pi f naught t. In this representation, a is the amplitude, f naught is the frequency, theta is the phase, whereas alpha, it contains the information related to both phase and amplitude. It is a complex number which is represented by a e to the power j theta. So, these complex sinusoid signals are really important for communication signals, because the first thing is that the phase and amplitude information can be captured through one complex number, and they also contain real sinusoidal signals. Like for a cos 2 pi f naught t, we can take the real part of the complex sinusoid, and that will be a cosine wave, and if we take imaginary part of the sinusoid, it will be representing a sine wave. Also, these complex sinusoid signals form basis for larger class of signals, that is, we can represent most of the signals which we are interested in as linear combination of these complex sinusoid. Another important class of functions is delta or impulse function. A delta function or unit impulse function, which is denoted by delta t, is a waveform which, mathematically speaking, is a unit waveform with a duration which is going towards 0. There are two examples which are shown here on the slides. You can see there are one representation is rectangular representation, another is a triangular representation, and in the limit when a is tending towards 0, this both will represent impulse signal. What does it mean is that impulse signal is a signal which is of unit area and has a width which is tending towards 0, implying that the amplitude or height of the signal goes towards infinity. This signal is not physically realizable, but it has some very significant properties which are very useful for communication signal analysis. One of this property is the shift property, which also is kind of a property which defines this signal mathematically. So, if we multiply a signal, continuous signal st with an impulse signal which is shifted at t naught, and then we take integral of st delta t minus t naught dt, then the resulting signal is going to be the value of the signal st at time t is equal to t0. What it means is that if we multiply any signal with impulse signal and take integral over the domain, what we will get is a shifted replica of the signal at the time where delta or impulse function is situated. This mathematical property will allow us to represent the signals in time domain as linear combination of impulses, and would be useful in analyzing time domain response of most of the communication signal and systems. Another form of signal which is very common and we will be encountering very often is sinc function. Sinc function by definition is sine of pi x divided by pi x. This function has time span which will be, if x is time, would be continuing from minus t to minus infinity to infinity t, and it takes maximum value of 1 and upper bounded by a value which is 1 over pi mod of x. This function would be very useful when we start analyzing communication signals. A system takes input one or more signals and produces output of one or more signals, but we are not going to talk about general type of signals. We will restrict our discussion here to linear time invariant signals, because most of the systems which are encountered in communication like filters, communication channels, they can be modeled as linear time invariant systems. Also, the input and output relationship of linear time invariant system is very easy to characterize and provides meaningful insights into the behavior of channels. So, how do we define linearity? Linearity can be defined by superposition. So, let us assume that there is a signal x1t which has an output y1t, and there is another signal x2t which has corresponding output y2t. Now, if we give an input of a1 times x1t plus a2 times x2t, where a1 and a2 are constants, then the resulting output would be a1 times y1t plus a2 times y2t. So, this superposition defines our linearity. Now, for time invariance, if we consider there is a signal xt which gives output yt. So, now if we give a time shifted replica of xt as input, which is denoted by xt minus t naught, then the corresponding output will also be shifted by same time. So, the corresponding output is going to be yt minus t naught. This is called time invariance. So, systems which have linearity as well as time invariance are called linear time invariant systems, and we will be mainly dealing with LTI systems. And the behavior of an LTI system can be completely characterized by its impulse response. The impulse response of LTI system is the output obtained through this LTI system when input to the system is an impulse signal. So, here are a few examples of linear systems. We can see the first system yt is equal to 2 xt minus 1 minus j xt minus 2 is linear, also time invariant. There is second example which is linear but time varying. Similarly, third example yt is equal to xt cos 100 pi t minus cos t minus 1 sin 100 pi t is a linear signal but time varying. And similarly, we can see the fourth example which is again linear and time invariant system. Now, we will see some examples of time invariant systems where the output will be shifted by the same amount when we shift input by a fixed time domain offset. So, now what we see here is the three examples where two of them are nonlinear and one is linear, and what we will be dealing in this course would be systems which are both linear and time invariant. So, output of linear time invariant system for input xt or ut is related to its impulse function or impulse response, which is denoted by ht, and this relationship between input and output is defined through a mathematical function called convolution, which is defined here, that output for a linear time invariant system yt, which has input ut and impulse response ht, is given by u convolved with h, and this convolution for continuous time signal is defined as integral minus infinity to infinity h tau u t minus tau d tau. If we look at this equation, it is very clear that this equation is symmetric in h and u. So, instead of ut being the input and ht being the impulse response, if we had a system which has impulse response ut and the input signal is ht, again the output will stay unchanged. It is going to be convolution given by integral minus infinity to infinity h tau ut minus tau d tau. So, here in this example we see how convolution is computed. So, we can see the first graph is x tau, which is the input signal, and second graph is h tau, which is the impulse response of the system. So, looking at the equation, like I said that we can have u and h changed. So, in this particular computation we are interchanging the position of h and u. So, what we are going to compute is integral minus infinity to infinity u tau h t minus tau d tau. So, that is why we convert first h tau into h minus tau, and then we provide by shift by value t. And in the next slide we see several instances where, like one case where t is smaller than 0, second instance where t is between 0 and 1, third instance where t is between 1 and 2, and third instance where t is between 2 and 3, and the last one where t is greater than 3. And in all these ranges, if we continue doing integral, we will get a trapezoidal function as the output of the system, which is given by h tau and input is x tau. Now, we come back to complex exponential. In the beginning, when we introduced complex exponential, we talked about how complex exponential can be used as a basis function to describe most of the signals which are useful for purpose of communication. So, this class of signals are extremely important, especially in the context of linear time invariant systems. This is what we are going to show here, that how this linear time invariant system and complex exponential relation allows us to describe the behavior of signals passing through communication channels, which can be modeled by linear time invariant systems in a very simple way. So, when a complex exponential passes through an LTI system, the output of the system is going to be another complex sinusoid having the same frequency, but having an amplitude and phase change. So, here we have shown that there is an input signal ut, which is complex sinusoid e to the power j 2 pi f naught t with frequency f naught, and it goes through an LTI system with impulse response ht. The output yt would be related to ut and ht in this form of convolution, and what we see is that we get output which is capital H f naught times e to the power j 2 pi f naught t, which means that the output signal is another complex sinusoid of frequency f naught with an complex multiplier, which will be changing the amplitude and the phase of complex sinusoid. So, for a complex sinusoid, we just saw that if input is frequency f, the output will also be of the same frequency, but scaled in amplitude and phase shifted. Now, this shifting and amplitude scaling can be represented by a complex single number h f naught. So, looking at the property of eigenfunctions, we can safely say that these complex sinusoids are eigenfunctions for LTI systems. which will allow us to characterize the performance of LTI systems for any given signal in terms of linear combination of complex sinusoids. So, here is an example how we can use this property of eigenfunctions of complex sinusoid to analyze performance of LTI system for any real signal. So, let us consider a sinusoidal input cos 2 pi f naught t plus theta and an LTI system with impulse response a e to the power minus a t, it is a exponentially decaying function. So, from Euler's formula we can write this cos 2 pi f naught t as linear combination of two complex sinusoids. Now, using the property that when complex sinusoids pass through LTI system, they are just scaled by a complex number, we can write the output corresponding to this sinusoidal signal through this LTI system as linear combination of the two complex sinusoids at frequency f naught and frequency minus f naught, and the corresponding channel values of h f naught and h of minus f naught. Simple mathematical analysis will allow us to compute this value of h f naught, which is going to be some constant frequency dependent amplitude scaling g and phase phi, both are defined in the slide, and the resulting output signal is going to be g times cos 2 pi f naught t plus theta, the initial signal, plus additional phase component phi. What it tells us is that if a sinusoidal signal passes through LTI system, we will get amplitude scaling by a factor of g and a phase shift by a factor of phi. In the next slide, what we have shown is that frequency dependent behavior. So, we have varied the frequency and what is the amplitude response of the system, and then in the next slide we see the phase response of the system. Your input signal as a linear combination of complex sinusoid allows us to do analysis of a signal passing through LTI system in a much simpler way. This example demonstrates how easily we can analyze how systems behave for different frequencies. Now, the question is, can we do something about writing each and every possible signal which is of interest to us as a linear combination of complex sinusoid? And this problem is solved by a mathematical tool called Fourier transform and its inverse. As you all would have studied earlier, that Fourier transformation of a periodic finite energy signal can be written as u of f is equal to integral minus infinity to infinity ut e to the power minus j 2 pi f t dt. There is a small condition which is required, it is that the signal has to be finite energy, and the Fourier transformation can also lead to representation of time domain signal in the form of complex sinusoid linear combination, which is given by inverse Fourier transformation, which is ut is equal to minus integral minus infinity to infinity u of f, which is the Fourier transformation of ut, times e to the power j 2 pi f t df, where e to the power j 2 pi f t are the complex sinusoids with frequency f. So, any finite energy signal can be written as a linear combination of a continuum of complex exponential with coefficients of the linear combinations given by Fourier transformation uf. This property will be one of the cornerstone for us to analyze further the response of communication channels which can be modeled as a LTI system for any signal. Here we consider few examples which will allow us to appreciate or understand how this real time signals can be represented as linear combination of complex sinusoids. So, first we consider a case of impulse signal. Impulse signal is denoted by pulse of 0 and height infinity with the area under the curve equal to unity, and when we take Fourier transformation we will get a constant. It means an impulse response is a linear combination of complex sinusoids of all the frequencies starting from minus infinity to infinity with constant amplitude value a. Another interesting Fourier transformation would be if you consider a gate pulse which is having non-zero value between minus t by 2 to t by 2 and the value is a, it can be written as a linear combination of frequencies which are from minus infinity to infinity, but their amplitudes vary with the sinc function. Something which is of very importance is the sine function, which we just now saw that using Euler formula we can write a sinusoidal function as a linear combination of two complex sinusoid function. When we take Fourier transformation of a sinusoid function, we get those two complex sinusoids as the Fourier transform pair. So, what we can see here is that the Euler's formula is just an special case of Fourier transformation, which can be applied to all the signals which are of finite energy, almost all the signals of finite energy, and not having discontinuities. To summarize, today we have studied some important signals which are used in communication systems and looked at their time domain description. Also, we have learned about linear time invariant systems which can be used as a model for most of the systems which are part of communication, like filters, and also can be used to model various communication channels like wired cables or free space propagation, and they allow us to describe the output of a signal in a very simple terms, in terms of a convolution of a input signal and the impulse response of the LTI system. We also looked at the complex sinusoids and the property that complex sinusoids are eigenfunctions of an LTI system. What it means is that when a complex sinusoid signal is passed through an LTI system, it will only have amplitude and phase shift, amplitude scaling and phase shift, and the frequency of the sinusoid remains unchanged. Meaning, if we can write all the input signals as linear combination of eigenfunctions, the output of the LTI system can also be written as the linear combination of the output to the different sinusoid functions of frequencies which are contained in the input signal. This analysis will be a cornerstone for us to understand the behavior of signal and understand what kind of distortions can be introduced on the signals when the signals pass through communication system, including filters and the channel. So, I hope that you enjoyed today's lecture.